Okay, next problem. We've got a thin, infinite, non-conducting sheet. Okay, with uniform charge density, sigma. Remember that sigma is charge per area. What we have here is planar symmetry. So we're going to end up using a pillbox, which is a cylinder, but it's you get flux out of the end caps instead of the shell. When you have cylindrical symmetry, you get the flux out of the shell. So your integral dA is a 2 pi r h kind of situation. And here we're actually just going to have some end caps. So we'll have those areas. So let's ask first, what does our electric field look like? And this is a positive charge, so it just looks like this. And people, it is a non-conducting sheet. So that means we got electric field coming out of both sides. When it's a conductor, the inside of the conductor is going to be 0. So that's nice. However, here, and I didn't mean for those to like look different on either side. They are trying to be the same. All right, let's change our colors. So we draw our Gaussian surface. So here we go. Boop, boop, boop. So this area, call that A. This area, call that A. Right? Same area. And you can call that whatever you want. You want to call it H? You go for it. But as you can see, there's going to be no... We always start with this, don't we? No flux out of the shell because our area vector is that way. And then the electric field is perpendicular to that. But our end caps, here's an area vector, and here is an area vector. So that's going to be real useful because the area out, the flux through the area on the right here is going to be EA, and the flux from the area on the left is going to also be EA. They both have the same sign. Your E and your A are in the same direction for both situations, right? So E dot A, and then your E dot A. Okay, cool. Now, how much charge is in here, right? So we're looking at like that amount of charge. My gosh, that's pretty. Sorry about that, guys. But because we have this relationship, we know that Planck is going to be sigma times A. So whatever that area of our Gaussian surface is. All right, we are cooking with gas here, people. So this, oh, look at that. Didn't matter about that dimension. We knew that. All right, so this is a lovely little result. This is the electric field near the surface of a thin insulating sheet. Okay? However, we're gonna take this a whole nother step. We are going to show you a very important setup for something else. Something that is particularly interesting here is that you will notice there is no dependence on R. So that means, right, so the electric field is uniform. Any finite distance away from the sheet of charge. Okay, so I know that might seem unintuitive, that no matter how far away you go, it's going to be this same uniform value. But think about a little bit about reality here. If this is an infinite sheet, then this is only going to be true that it's an infinite sheet when you are close enough to the surface so that that looks infinite. Okay, so this is true for an infinite sheet, and again, it just means that we're close enough so that r is much, much less than whatever dimension that is, if you want to call it L. Okay? All right.